Hello, this screencast is to help you with the Module 11 homework, Introduction to the t-Statistic, which is Chapter 9 in the Graviter and Wallano Statistics book. So I will point out that some of your actual numbers in the assignment may be different or they may be not different, but the general idea for all of these assignments is the same. So the steps you would follow would be identical, just the numbers may or may not be different. Okay, so let's look at the first problem here, which is problem 6 out of the Graviter and Wallano book. Problem 6 says find the t-value that forms the boundary of the critical region in the right-hand tail for a one-tailed test with alpha at 0.01. And it's giving you 3 problems to solve with 3 different sample sizes. So the thing to remember to solve these problems is that you need to use the t-distribution table found on page 651 in the Graviter and Wallano book. Remember that to use t, sample size is no longer a concern because every possible distribution from sample size of 1 to 120 has already been calculated by statisticians, and their critical region values have been put in this table for us. So all of the n's less than 120 are actually all the degrees of freedom, which are based on n, or sample size, less than 120, with the assumption that any sample size over 120 would be normal, is included in this t-table. For a refresh on what the t-table looks like, on page 651 you will see degrees of freedom over here, and degrees of freedom are calculated by subtracting 1 from the sample size, or n, and then looking, depending on if you want the proportion in a one-tailed test or for a two-tailed test. So let's just say I want to look up alpha set at 0.05 for a two-tailed test. And of course here I have something else highlighted, but I would go to the proportion in the two tails, look at 0.05, and let's say I have 4 degrees of freedom. So I would go to degrees of freedom 4. Now think about it. How many are in the sample if I have 4 degrees of freedom? It's n minus 1 to get degrees of freedom, so I would actually have n equal 5. But I'm looking up 4 degrees of freedom in the table, and I want to look at alpha set at 0.05 for a two-tailed test. So I'm going to come over here, and it's going to be this value right here, 2.776. If it was a one-tailed test, alpha set at 0.05, then I would use this column here, degrees of freedom 4, and 2.132 would be my critical region. So the critical value or critical region is published in the t-table. And remember, t is going to work just like z, where you have a t critical value, this value from the table, and you're going to compare your calculated t, or your obtained t value, with this critical value. If t obtained is greater than this value, either positive or negative, then you can reject the null. If it's not greater than, then you can't reject. Okay, so let's go back up here and look at that. So basically what we're going to do is we're going to use the t-table. We're going to calculate degrees of freedom for each of these n values, and then look that up for alpha equal 0.01 in a one-tailed test. That means you're going to be looking alpha 0.01 in the proportion in one-tail row, which is right here. So you're going to be looking for whatever your calculated degrees of freedom are in this specific column here. Okay, so that's how you solve part A, B, and C in this first problem, problem 6. Let's go to the next problem. Now, you'll notice that there's actually only 2 more problems on this assignment, 14 and 16. These are long problems, though, with multiple steps, especially 14. So what I'm going to do in the screencast is walk you through each step. Okay, so we have this situation. We have animals, including humans, who avoid direct eye contact. A researcher was conducting a study to see how eye spot patterns affected the behavior of birds. They recorded the amount of time each bird spent in a plane chamber during a 60-minute session. And the study produced a mean of 34.5 minutes on the plane chamber side, and it's giving you the sums of squares value of 210, and this is with a sample of n equals 15 birds. The value in the population is a mean of 30 minutes in each chamber. And the standard deviation in the population is not given. It's probably unknown. Or for whatever reason, it's not given here. So we are ultimately going to be comparing this mean of 34.5 to a mean of 30 minutes given this measure of variance, sums of squares in n equal 15 birds. Okay, so there's 4 steps to the hypothesis test, and part A is asking you to hypothesis test. Is 34.5 significantly different than 30 minutes in these 15 birds, given this variance in these 15 birds? Okay, or measure variability. Okay, so first we have to identify the 2 hypotheses. Let's start there. Okay, remember, this is a long problem, many steps. And because of that, there's only 2 more problems on this assignment, but here's how to solve. So first we need to identify the hypotheses. This is the same way you've been identifying hypotheses in the last 2 chapters, and there's good examples in practice problems 9.1 and 9.2 in this module. This particular problem is asking for a two-tailed test with alpha equal to 0.05. So just state your null hypothesis and your alternative hypothesis for a two-tailed test. Okay, next we have to determine the critical region. Here's where we need the value in the t-table. Again, that t-table is on page 651 in the Graviter and Wallano book. And here we need to calculate degrees of freedom based on sample size and use those columns for the two-tailed test where alpha is set at 0.05. Degrees of freedom is n minus 1, and the value in the t-table is your t-critical value. And again, a refresh, if your obtained t-value that we're going to calculate in the next step is greater than t-critical, we can reject the null and say we have a significant effect. If our obtained t-value that we calculate in the next step is less than t-critical, we cannot reject the null. I'll also mention too that we have had problems in the past where t obtained equals t critical. So what do you do then? It's actually up to you to decide if you're willing to reject the null or not. Technically, it should be greater than in order to reject the null, but I have seen researchers reject the null if it's equal. Okay, so now let's do step 3. Calculate the t-statistic. And how do we do that? Well, we have to use this formula. So our formula for t is the mean of the sample minus the mean in the population divided by the standard error of the mean of the sample. Now, how do I get standard error of the mean of the sample? Standard error of the mean of the sample equals the square root of the variance of the sample divided by n of the sample. Well, how do I get the variance? Variance is calculated by using sums of squares divided by n minus 1. Or sometimes you see this as sums of squares divided by degrees of freedom, right? Because n minus 1 is degrees of freedom. Now, because sums of squares is given to us, we don't need another formula for that. If sums of squares is not provided and we have to calculate it, there is another formula for that. I'll refresh your memory. You've seen it. It's here, actually, on the practice problem where we had to sum x anyway. So we don't have to do that in this particular problem, but there is a formula if you need it. All right, so then you just plug in your numbers, do your calculations. I recommend starting with sums of squares or getting the variance first because you're going to need this variance in order to calculate standard error of the mean of the sample, and then you'll be able to do the t. Now, the other helpful tip I'm going to give you here, show your work for every single step. So put this formula, again, you could just type it out, right? How would I type it out? I would say s squared equal, and I don't care if it's capitalized when you're doing this in Word, sums of squares divided by n minus 1, and then that would equal 210 divided by the degrees of freedom was 15 minus 1, which was 14, and then you could just do that math. But save your work for each part of this because you are going to need these values in later questions. There will be later problems that ask you for the variance, and you don't want to calculate that again. There's another problem that's you're going to need standard error, the mean of the sample. You don't want to calculate that again. So again, just, oh, and then how would you solve this using Word? You could just type in SM. You scroll down a little so you can, well, I guess you can't see both that way, but SM equals square root, you could abbreviate it, of s squared divided by n, and then you could solve that. Square root of whatever that s square valued was, and so forth. So you can type those out, but again, helpful tip, keep those answers handy. Okay, so that was a lot, but SS was given, so you just do that math. All right, you will get a t value and then just compare your t obtained to the t critical value as explained above. So that's pretty easy, right? You've gone through these 4 steps already. You've identified your 2 hypotheses, you've determined the critical region, you've calculated the test statistic, and you've used that test statistic to make a decision, and you've interpreted the decision, which is I reject the null, I have a significant effect, or I do not reject the null, I don't have a significant effect or a significant difference between these means. Okay, now to part B. So part B asks you to compute the estimated cones D to measure the size of the treatment effect, interpret that cones D, and then compute and interpret the R squared as a measure of treatment effect or effect size. So to do the first part of this, cones D, just use the formula for cones D. Remember I said you'd want S later? Well, wait a minute. Where do you get S from? Well, remember you calculated S squared up here. So to get S, just take the square root of S squared. And then you can plug in that number. Should be a very simple formula. Subtract the means and divide by S. Then use these rules for interpreting the magnitude or effect size. 0.2 is a small effect, 0.5 is medium, 0.8 or above is large. The formula for R squared then is also quite simple. Use your obtained t value here. Now t here is the obtained, your calculated t value, square it, and then divide by t squared plus your degrees of freedom. Just do the math. Here's how you interpret the magnitude of R squared. If R squared equals 0.01 or less, you have a small effect. If it's 0.09 to 0.01, you have a medium effect. If it's 0.25 or above, you have a large effect. And so just kind of use your best judgment there. Like if it's 0.21, is that large or medium? It's medium. If it's 0.05, is it it's not yet medium, so it would be a small effect. Also, when you're interpreting R squared, make sure you're relating that value to the percentage of variance explained by the treatment. And we can look at practice problem 9.2 to see what I mean with that. See in this problem, R squared was calculated at 0.417 in this particular problem. We can use this to interpret like, okay, so 0.41 is a pretty large effect size because it's greater than this 0.25 cutoff. But what does it really mean? R squared is a neat statistic, and we're going to see it again when we do correlations. It's actually allowing us to determine how much of the difference in scores between M, mean of the sample, and mu, mean of the population, how much of the difference in those scores or the variability between those scores is caused by the treatment that we gave. For example, in this problem with the birds, how much of it was caused by being in the plain side of the chamber, and so forth. And so use this as an example for how to interpret R squared. But R squared is telling us how much of the variance in scores is explained by the treatment. Okay, so let's go back. We have one more part to the homework. We've done cones D, we've done R squared. Now we have to do the confidence interval. This particular problem is asking us for the 90% confidence interval. Typically, we do use like 95 or 99% confidence interval, but I'll show you how to do 90% just in case it shows up, and then talk about how to interpret that. So confidence interval is telling us, is giving us an estimate of where we would expect to find the mean the next time we ran this study is kind of a good way to think about confidence interval. To calculate it, you just use the formula, and you saw this formula in practice problem 9.3. The formula is, and I would actually, usually I represent this with a CI or confidence, and I would put CI 90%. But if you want to put the mean there, that's fine too. But the value is going to equal the mean of the sample plus or minus t critical, the critical value for t given your degrees of freedom, and this multiplied by the standard error of the mean. Okay, so we have a couple things going on here. First of all, I'll mention again, standard error of the mean was calculated above, right? So when I gave you the tip to make sure that you saved your work for all these, save your answer, you don't have to calculate that again. Phew, saved yourself a bunch of steps. Now what about this T critical? Here's where people get confused. They have a critical value above that may or may not be accurate here. The important thing to remember for critical value, or the confidence interval, is that we always have to use the two-tailed value, even if you conducted a one-tailed hypothesis test. Why? Well, this is because the confidence intervals are trying to give an estimate of values on both sides of the mean, right? The range of scores for the mean that we might expect to see if we run this test again. So we want to look at both tails or both sides of the mean. So even if you run a one-tailed test for your hypothesis test, to get the confidence interval, always, 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 always use the two-tailed value. I will tell you, if I ever see mistakes in confidence interval, it's because people use the wrong critical value for t. So that's my helpful tip. Once you understand that, you just use the degrees of freedom. These are the same, right? Because your n is the same. So for this problem, degrees of freedom was 14. And look up the t critical value for the two-tailed test at the alpha level set in the problem. Now, by problem here, I mean what confidence interval, not what you tested your hypothesis at. So if the confidence interval is asking for a 95% confidence interval, we want to use alpha at 0.05, right? 95%. If it asks for 99% confidence interval, use alpha at 0.01. And if it asks for a 90% confidence interval, like this problem is, use alpha set at 0.10, 10%, right? So again, that's the biggest tip I could give is separate confidence interval from your hypothesis test above. Okay, so once we do that, we can look. Now we actually we have degrees of freedom of 14 in here, so we don't have the actual value that we need for t-critical, but I do want to use the two-tailed test at alpha set at 0.10, so this highlighting in green, and I would just scroll all the way down to degrees of freedom of 14 and use that t-crit value, plug that into this number, do the math, right? Solve, make sure you're following the order of operations, that is multiply the t-critical you just looked up by the standard error of the mean of the sample you calculated earlier, and then subtract that value, add and subtract that value from the mean to get the range of scores. And then answer with the range of values and interpret it just like you did in practice problem 9.3. And the answer there was we are 95% confident, but here we're 90% confident, right? Because we did a 90% confidence interval. So we would be 90% confident that the true population mean for, in this problem we're talking about number of minutes birds spent in a particular chamber, falls between whatever these calculated values were. Okay, woohoo, we are done with that problem. The next problem is absolutely identical, but the only difference is you're actually given S, so you don't need to calculate it. Just use the other formulas above and plug in S where needed. So you're using the same T. You are squaring S provided and dividing by N and then taking the square root of S to get your standard error, the mean of the sample. You're plugging that in. So this problem is actually leaving out this step. And what else? I don't believe you're going to have to do Cohen's d, R squared, or confidence interval in this problem. So enjoy the break. All right, the Excel problem's covered in another screencast. If you get stuck or have any questions, reach out for help. Thanks.